We have spectacular photographs of the planets in our solar system. Some of them are taken from telescopes located on the Earth or in space, or from probes we actually send to orbit these planets. But outside of our own solar system, there are thousands of other planets discovered orbiting other stars. Objects that we call exoplanets. They are too far away to send a probe to, or ever get a clear picture from a telescope. And so it's the role of artists to help us imagine what these worlds could look like. I'm Robert Hurt. I'm an astronomer, but I'm also an artist. And part of my job is to help illustrate things that we have discovered scientifically, but cannot yet take really clear photos of, like exoplanets. And today, we're going to explore the process of how we go from the science of a discovery into creating a piece of art that captures that, but goes beyond to inspire us. So to explore how we illustrate exoplanets, we're going to look at one particular system called TRAPPIST-1. Now, this is a very interesting system because it has a total of 7 planets that have been discovered that are each more or less the size of our Earth, orbiting a star that's very small and cooler than our own sun, just a little bit bigger than Jupiter. So, how do we even know that this distant star that's so far away it takes light 39 years to reach us has planets? Well, there are a lot of different techniques astronomers use to discover planets around other stars, but one of them is actually pretty easy to understand. It's called the transit method. So imagine that this is a star. This is a distant star. Now, we can't actually get a sharp picture of it. It's just a blur of light. Even as a star, it's too small for our telescopes to be able to see it as a disk. But we can measure its brightness, and we can measure its brightness very carefully. But let's imagine there's a planet orbiting a star, and it's got just the right orbit that, from our point of view, every time it goes around the star, it will briefly pass in front of the star from our perspective. And during that period of time, the planet is going to block a little bit of the star's light. That's something that we can measure. And so as it continues its orbit, we will see that the star will get briefly dimmer for this short period every time the planet orbits. It turns out there's a lot we can figure out from this. For one, when the planet is blocking the star's light, how much of that light is blocked directly tells us how large the planet is, so we can measure its radius just from the amount of light that it blocks. We also know how often it passes in front of the star, and from that timing, we know the length of the planet's year. From that, we also can calculate how far away the planet is from its star, and that tells us whether the planet's going to be very hot if it's near the star, or very cold if it's far away. But in the TRAPPIST-1 system, there's another thing we can measure that's very hard to do in most cases, and that's because these planets orbit very close to one another. In fact, sometimes in the TRAPPIST-1 system, the planets pass so close to one another in their orbits, they're only a few times further apart than we are from the moon. And that means the gravity of these planets drags them. They can speed them up or slow them down in their orbits, and that changes the timing of how they pass around the star. By measuring those slight changes in timing, scientists can actually calculate just how massive these planets are, a trick that's very hard to do for most exoplanets. So now we know how big the planets are, we know how far away they are from the star, how warm they are, but we also know how massive they are. And from their size and from their mass, we can calculate their density. And density is the first step towards understanding what a planet is made of, what its composition might be. Knowing as much as we did about the TRAPPIST-1 worlds really gave us an advantage when it came time to try to imagine what these worlds could be. Using the data we have in hand, the scientists decided that one interesting feature of these planets is that they could possibly be tidally locked to their star. This means that they would always have one side of the planet facing the star and one side always facing away from it. So depending on where you were on that exoplanet, you would either be in perpetual daylight or in perpetual darkness. That means that when we illustrated these worlds, we wanted to show that there was a potential difference in what the planets looked like on the perpetually hot side versus the perpetually cold side. So for the inner two planets, B and C, we just adopted a basic idea that they would be hot, possibly very dry, maybe very little atmosphere. So we just had rocky fairly nondescript worlds. But it got interesting once we got to TRAPPIST-1D, because this starts to fall in the temperate zone of the system, where liquid water potentially could exist on the surface if other conditions are right. But because of this hot-cold dichotomy, there was a kind of idea for an exoplanet called an eyeball planet. This is the idea that there's a Goldilocks zone that might exist between the side of the planet that's too hot and the side of the planet that's too cold, where right between them, you might have a just right zone where liquid water would exist. So for TRAPPIST-1D, we actually put liquid water, signs of water, right around that day-night divide between the two sides. Moving on out to TRAPPIST-1E and F, the models suggested that they could potentially be what we call water worlds that have a high fraction of water, many miles deep, all across their surface. So we showed them as being covered by water. E, a little warmer, a little more liquid. As you go further out, F got a little icier. And likewise, other models for G and H as we go out in the system. Over time, we learn more about the system and new ideas come up. So the artwork itself has to change to reflect those ideas. By a few years later, we've actually changed up the system to reflect a whole new set of ideas of what the planets would be. By 2021, scientists had continued to study these planets, measuring their orbits again and again, and refining the estimates of their masses and their densities. And this changed around models for what the planets might be like. In particular, one thing that changed between 2017 and 2021 was the idea that maybe these planets aren't actually tidally locked to the star. And that came about because of the considerations of the strong gravitational influence they have on one another. It might be enough to disrupt that. And so, as a result, we went away from this eyeball world kind of model to one where the worlds were more uniformly distributed. So let's look at how the artwork changed in 2021. First of all, for TRAPPIST-1B and C, we shifted away from the dry, bare world to a model based more on Venus, a thick atmosphere with thick clouds. This was a direct result of having improved measurements of mass, particularly in the case for TRAPPIST-1C, which began to match Venus very closely in its size, density, and heating from its star. Now, TRAPPIST-1D shifted a little bit out of the scope where we thought it was likely to have a lot of water on its surface, so now we just shifted it to more of a dry, rocky world. It started to share more similarities with Mars, including size and density, though it would likely be quite a bit warmer. That led to the possibility that, like Mars, it too might have lost most of its atmosphere. TRAPPIST-1E, however, got interesting. It shifted more into what we thought was compatible with an Earth analog, having a similar density, having a similar temperature profile as Earth. So if the other conditions would be right, it could potentially support liquid water on its surface. So this one we showed with oceans and land masses. Now for TRAPPIST-1F and G, we maintain the idea there could be water there, but because they're further out and colder, that water was shown increasingly in the form of ice on the planets. And TRAPPIST-1H became something maybe closer to Mars by our analogy. That's because it also matched the red planet very closely in its size and density. But scientific study continues, and with NASA's launch of the James Webb Space Telescope, we now have an important new tool in our science arsenal to study these worlds. Now, at the time of this recording in 2025, a lot of work has been done on the innermost worlds, TRAPPIST-1B and C, and careful measurements of their light as they orbit the star have now suggested they probably don't have any atmosphere at all. So we've backed away, and other artists have taken new inspiration from this to show them closer to the way we would expect Mercury or the Moon to look like, as airless, barren worlds. So as we can see, no piece of science-inspired art can really be considered the final story, because research will always continue, and as we refine our understanding of what these worlds might be like, we will have to update the artwork to reflect that. But that's part of the fun, and that's part of the process. When you see a beautiful picture in Exoplanet, you know that's the work of an artist, because we're generations away from capturing data that matches the same quality as the pictures of planets in our own solar system. But that's great, because it means artists are going to continue to play a vital role in science communication, in taking the broad brushstrokes that come from the research, then filling in the gaps that capture our imagination and inspire us to learn more.